All right, welcome to The Explainer. Today, we are diving headfirst into this massive, high-stakes race to secure our entire digital world from a totally new kind of threat. And yeah, that sounds pretty urgent, right? Because it is. There's a new kind of computer coming, and it's not just an upgrade. It's about to completely rewrite the rules of digital security as we know it. So we're kicking things off with the quantum threat. And look, we're not just talking about a faster computer here. This is a machine that runs on the frankly bizarre rules of quantum mechanics. And it's on track to shatter the very foundation of all modern encryption. And get this isn't some far-off science fiction fantasy. Experts are estimating that the first truly powerful, error-corrected quantum computers could be here as soon as 2030. So yeah, we are on a deadline. A very real one, to prepare for a technology that could leave our most sensitive data completely out in the open. So, how are these things so powerful? To really get the threat, we have to understand what makes these machines tick. And it all starts by rethinking the most basic piece of information, the bit. Okay, look at this. Your computer, right now, uses bits. A bit can be a 0 or a 1. Simple. But a quantum bit, or a qubit, it can be a 0 and a 1 at the exact same time. That little word "and" changes everything. A regular computer has to check one possibility after another, one by one. But a quantum computer, it gets to explore a whole universe of possibilities all at once. This mind-bending property is called superposition, and it's the secret sauce behind a quantum computer's power. Think about it like those ripples on a pond. They can overlap and create these incredibly complex patterns. That's kind of what a qubit does, but with information, letting it explore this vast landscape of potential answers simultaneously. And this is where it gets really crazy. This power grows exponentially. A 50-qubit quantum computer can handle 2 to the power of 50 states at once. Now that's a number so huge, it's hard to even wrap your head around it. We're talking about a number so big that not even the most powerful supercomputer on Earth today could ever hope to match it. It's not just a step up, it's a monumental, game-changing leap in power. Okay, so you've got this incredible new power. What do you do with it? Well, with new power come new weapons. And there are 2 quantum algorithms in particular that are like perfect code-breaking tools, aimed directly at the encryption that protects, everything. Your emails, your bank account, all of it. So here are the 2 big villains of our story. First up, you've got Shor's algorithm. This thing is a wrecking ball for asymmetric crypto. That's the stuff we use for secure handshakes online. You know, the padlock in your browser? Shor's doesn't just weaken it, it absolutely destroys it. Then there's Grover's algorithm. It goes after symmetric crypto, which is the workhorse we use to encrypt the actual data. It doesn't destroy it, but it weakens it a lot. So what's the aftermath? Well, the good news, if you can call it that, is that we can sort of salvage symmetric encryption. We just have to double the key sizes, go from AES 128 to AES 256, and we're basically back to being secure. But the really bad news? That asymmetric encryption, the public key system that the entire internet's security is built on, Shor's algorithm breaks it completely. It's not a matter of patching it, it's fundamentally broken. We need a whole new foundation.
All right, enough doom and gloom. Let's talk about the solution. Because thankfully, the world's smartest cryptographers haven't been sitting on their hands. They've been building a new generation of defenses, something called post-quantum cryptography, or PQC for short.
And the goal of PQC is, simple in concept, but incredibly profound. The idea is to find brand new mathematical problems that aren't just hard for our current computers, but are incredibly difficult for any computer to solve, and that includes those super powerful quantum computers. So, you know how current encryption relies on problems like, find the 2 prime numbers that multiply to make this giant number. Well, it turns out quantum computers are amazing at that. So we're throwing that out. The most promising new candidates are based on a totally different kind of math. It's called lattice-based cryptography, and it's all about the geometry of dots in really, really high-dimensional space. Okay, security in a lattice, the surprisingly hard math of dots. So, how on earth does this work? Well, it all starts with a surprisingly simple picture, just a repeating grid-like pattern of dots. That's a lattice. Now, the security of this whole new system comes down to solving one specific puzzle, called the closest vector problem. Imagine you have this lattice stretching out in hundreds of dimensions, and I drop another point somewhere in that space. Your challenge is to find which dot on the lattice is the absolute closest to the point I just dropped. Sounds kind of simple, right? Well, it turns out to be so incredibly difficult that we believe even a quantum computer would get stuck trying to solve it. So here's the clever part. The secret is all in the basis, which is basically the set of directions you use to describe the lattice. If you have the private key, you get what's called a good basis. The vectors are nice and spread out, almost at right angles. It's like having a perfect, clean grid map. Finding the closest dot is super easy. But the public key, that's the bad basis. The vectors are all skewed and nearly parallel. It's like a warped, distorted map where everything looks stretched out. Using that map to find the closest dot is insanely hard. And this is how it all fits together into this really elegant system. Here's how it works. Step 1, Alice creates her lattice. She makes 2 maps, the good one, which she keeps secret as her private key, and the bad one, which she publishes as her public key. Now, Bob wants to send her a secret message. He uses her public bad map to encode his message as a point near one of the lattice dots. Now, only Alice, with her secret good map, can easily figure out which original dot the message was close to and decode it. Anyone else, any eavesdropper who only has the bad map, they're just left staring at an impossibly hard math problem. It's brilliant. Okay, so we have the solution. This lattice stuff works. So what's the rush? Why the big race against time if these quantum computers are still a few years away? This brings us right back to that quote from the beginning. Here's the problem. It's a strategy called Harvest Now, Decrypt Later. Right now, adversaries can be intercepting and just storing all of our encrypted data, hoarding it. They can't read it today, but they're betting that in a few years, they'll have a quantum computer that can. Think about data that needs to stay secret for a long, long time. Government secrets, your company's intellectual property, your personal health records. All of that is vulnerable today. And that's why the global rollout is such a massive, urgent undertaking. The National Institute of Standards and Technology in the US, NIST, has been leading the charge. They started this huge competition way back in 2016 to find and standardize the best quantum-resistant algorithms. After years of testing, they finally picked the first winners in 2022. And this year, in 2024, the first official standards are being published. All of this is in a race to get ahead of 2030, which is when many experts think that these quantum computers will become a real threat. And the results are in. And guess what? 3 of the first 4 algorithms that NIST chose are all based on that lattice math we just talked about. This really shows how much faith the cryptographic community has in this approach. We now have new standards for different jobs. There's CRYSTALS-Kyber, which is for general-purpose encryption, and then there's CRYSTALS-Dilithium and Falcon, which are for digital signatures. And those are absolutely essential for proving who you are online. So that leaves us with this huge question. Our entire digital world, everything we do online, was built on one kind of math. Are we ready to tear it all down and rebuild it on a completely new one? Because the transition to post-quantum cryptography is going to be one of the biggest, most complicated upgrades in the entire history of the internet. But it's a race we simply cannot afford to lose. Thanks for joining me on this explainer.